Okay, so in this video, we will try, if possible, to evaluate the given improper integral of type 2. Clearly it cannot be of type 1 as we have finite bounds of integration, but if it is of type 2, there has to be a discontinuity. Well, we have a rational function. The only possible discontinuity is a division by 0, and clearly here if x equals 3, we have a division by 0, and 3 is between 2 and 5. And so we have a unique discontinuity at x equals 3 in our range of integration. And that is why this is an improper integral of type 2. Well, as always, to get a feeling for what this may look like, we'll sketch the graph of the function between x equals 2 and x equals 5. Now, since when x equals 3, and notice that one simple observation, since we have x minus 3 squared, this is always positive, 1 over something positive is positive, so between 2 and 5, or actually over the entire real line, we have a function that is always positive. But when x equals 3, we have a 1 over positive 0 case, which will give us positive infinity. So once again, as in our previous examples, we have a vertical asymptote. Now you can plug in here x equals 2, which will give you 2 minus 3 negative 1, squared is plus 1, so the y value is 1. And at 5 you have 5 minus 3, 2, 2 squared is 4, you have 1/4. And now if you look between 2 and 3, as x gets closer and closer to 3 from the left, this will shrink to 0, you'll have 1 over positive 0, so it will blow up to positive infinity. So the graph will look something like this. And if you look here, as you go from 5 to 3, well again, as as x approaches 3, this will approach 0 squared, which was positive. You'll have a 1 over positive 0, so this will also approach positive infinity. So the graph will look something like this. Okay, so now we have the graph of our function between 2 and 5, and we have an infinite discontinuity at x equals 3. What is interesting about this problem is that in our previous two examples, in the first, the discontinuity occurred at the right-hand point of our interval. In the second example, the discontinuity occurred at the left-hand point of our interval. Now, the discontinuity occurs in between our two endpoints. And so this will require a little bit of extra work. We're trying to integrate this function from 2 to 5, but we cannot jump over this discontinuity. We have to avoid it first. So let's see how we can do this. So let's start over here. So from 2 to 5, 1 over x minus 3 squared dx equals. Well, we're trying to go from 2 to 5 again, but we can't jump over our discontinuity. We have to avoid it. So we have to go from 2 to, say, t, stop a little before, so as we integrate from 2 to t, our function 1 over x minus 3 squared, then we'll have the exact area below our curve between 2 and t. And to complete from 2 to 3, we will have to let t get closer and closer to 3. So we have to take the limit as t approaches 3. And again, if we leave it like this, we're wrong, because we have to specify that t approaches 3, but from the left. So t must always be slightly smaller than 3. So t approaches 3 from the left. So now we have the first half of our improper integral plus, what about the second half, from 3 to 5? Well, we can't start at 3 again, as at 3 we have an infinite discontinuity. So we have to avoid 3. We have to start a little after 3, say s. And now between s and 5, we no longer have a discontinuity, and so we can integrate no problem. So from s to 5, 1 over x minus 3 squared dx. But once again, that's not all of it, right? We have to then let s approach 3 from the right. And now, in the limit, both parts will complete the entire improper integral. And so you see, when you have a discontinuity that is not at one of the endpoints of the interval, then you end up with two limits of definite integrals. And of course, the only way for the improper integral to exist, to converge, is if both limits exist. If you try to evaluate at the first, whichever one you choose, and it doesn't exist, then you're done, the improper integral diverges. If both limits do exist, then their sum will give you the value of the improper integral, and then we'll say that this converges. So let's try and look at the first limit. As always, all we need, because now from 2 to t our function is continuous, and so we can use the fundamental theorem of calculus, and all we really need is an antiderivative. Well, this can be accomplished with a very simple u sub, letting u be equal to x minus 3. Then the differential of u du is dx, as the derivative of x minus 3 is 1, and the integral becomes essentially trivial. We have 1 over u squared du. Rewrite 1 over u squared as u to the negative 2. Use the power rule. And go back in terms of x. Now that we have our antiderivative, we can evaluate this definite integral with the fundamental theorem of calculus. So we will evaluate our antiderivative, leaving the plus c out, so negative 1 over x minus 3 from 2 to t. So let's plug it in. Our antiderivative at t, so we get negative 1 over t minus 3 minus minus, so plus 1 over 2 minus 3 let's simplify a little bit here. So 1 over 2 minus 3 is 1 over negative 1. So it's just negative 1. It's a constant. It can be pulled out of the limit. So we have negative 1 plus. And here, if I want, I can put a negative here and do 3 minus t instead. So the limit, as t approaches 3 from the left, of 1 over 3 minus t. And we can look at what kind of case we're in. 1 is 1, no matter what. And look at the real line. We have 3. As t approaches 3 from the left, t is very close to 3, but slightly smaller than 3. So if we do 3 minus t, then it is positive. As t is larger than t, 3 minus t is bigger than 0. So we have a 1 over positive 0 case. But 1 over something that shrinks to 0 always positive will blow up to positive infinity. So in the end we have negative 1 plus infinity, so it's just positive infinity. So the limit doesn't exist. If we go back to our first limit of a definite integral, we have just found that this limit is equal to infinity. So if you look at the given picture, the area below the curve between 2 and 3, the whole thing, if we include now the portion that shoots up to positive infinity, this area is infinite. And so because the first limit doesn't exist, then the original improper integral simply diverges. You could have also started with this one first, and you would have arrived at the same conclusion. This is also positive infinity. So it never matters which one you start with. As soon as one diverges, you're done. The original improper integral diverges. If both limits do exist, then the improper integral converges and is equal to the sum of the two limits. And that's it. Now, one last comment, and that is, from now on you have to be very careful that you keep in mind to look for discontinuities of the function you're integrating over the interval that you're integrating over. Suppose we ignore the discontinuity here, and we miss it, and we simply assume, because we're missing the discontinuity, that everything is fine, and we apply the fundamental theorem of calculus directly. Let's see what happens. So let me reproduce quickly what we had. We had the following picture. And we were aware of our discontinuity. But suppose we do not notice it. And we say, okay, well, we're trying to integrate from 2 to 5, 1 over x minus 3 squared dx. Recall that with a simple u subletting u be x minus 3, we find that the antiderivative of 1 over x minus 3 squared is equal to negative 1 over x minus 3 plus c. So this we have done previously. Now we can apply, again, if we overlook the discontinuity, the fundamental theorem of calculus. So we have our antiderivative, and we evaluate from 2 to 5. So what do we have? Negative 1 over 5 minus 3 is 2, minus minus, so plus 1 over 2 minus 3, negative 1. So we have negative a half, negative 1, negative 3 half. And so on the surface, everything is fine. We have our function, we found its antiderivative, evaluate at both endpoints, subtract, and you have the answer. But the key point is here we made a crucial mistake. We can only do this, go directly from the definite integral to its antiderivative, and then evaluate, if the function is continuous on its interval, which clearly it isn't. So this is simply wrong. And so I leave you with this, a simple word of caution. From now on, before you evaluate or try to evaluate a definite integral over a finite interval, always look for discontinuities, because we have just shown that this integral actually is infinite. It does not exist. It diverges, but if you skip over the discontinuity, you get an answer which actually is completely wrong. So always be careful that you do not miss discontinuities of the function you're trying to integrate.